So I believe most of you are aware of the hardware concepts which are used in real-time system. For some of you, it may be a refreshing module probably, and some of you, if you don't have much idea, definitely it will give you a lot of insight in the hardware which are used for real-time system. Okay, so what is the motivation? So many real-time systems are embedded systems. Okay, so embedded systems interact closely with specialized input and output devices, including sensors and actuators, right? So what are the input to an embedded system? The sensors, the input signals from some kind of sensor, and output will be finally the output signal to some kind of actuator or display or whatever it may be. Okay, and the hardware structure can affect timing and require special software design techniques. So depending upon the hardware, the software design will be affected definitely, and real-time system engineers must have some familiarity with the hardware to do some low-level programming. So whoever actually does software programming at the level, the system level, or the level which is very close to hardware, they must have knowledge about the underlying hardware, otherwise they cannot write appropriate software code for this. Okay, these are some of the motivation, of course. So this hardware, if you see, has multiple things. It has multiple components. Any embedded system you take, it will have a processor, it will have memory, and it will have peripherals, different peripheral chips. So we will our discussion flow will continue in that direction. So we will start with understanding the processor or recalling the processor architecture, I would say. I assume that you people are familiar with processor architecture, memory architecture, and the peripherals. So it is more of a refreshment of those. So we will start with understanding and remembering whatever we have learned, and if anything new is there related to the processor architecture. Okay. So the processor architecture is primarily of two types. It is von Neumann and Harvard. Okay, so what is a von Neumann architecture? So a von Neumann architecture, it started by the physicist John von Neumann and of course others in 1945, while he designed the the computer EDVAC. Okay, so this is also known as Princeton architecture. So what is the basic principle of this von Neumann architecture? Here, CPU is connected to memory and I/O through system bus, and I/O is also memory mapped. Okay, so you can see that one CPU is there, one memory is there, one I/O is there, CPU and memory, there is one bus is there. Okay, so basically in the system bus there is one unidirectional address bus, bidirectional data bus. Why address bus is unidirectional? Because CPU will send the address to the memory. Okay. Memory is not going to send back the address. Memory will send back the data. Then why data is bidirectional? Because CPU sometimes will try to read the data, sometimes CPU will try to write the data. So when CPU will try to write the data will flow from CPU to memory. When CPU will try to read the data will flow from memory to CPU. So that's why data bus should be bidirectional. And of course you need a control box. This control bus will contain different signals. For example, if you want to send a read signal, so it will be a part of the control bus. If you also it will send some starter signals as well. Okay, and the power line should be part of this control bus. So this is a basic von Neumann architecture. Okay. So we talked about von Neumann architecture. Then what is Harvard architecture? We talked about CPU. We talked about memory. We talked about I/O. Then what else is there? Okay. Then why there is something called Harvard architecture? The Harvard architecture has, again, it has started with Harvard Mark, which basically are the relay-based computers. Okay. So here data and address bus are separate. You can see the system bus has one address bus, one data bus, one control bus. That is one bus. But in this case, there is a separate data bus, there is separate address bus. So it is possible to access program memory and data simultaneously. That way, improving the speed. Here there is only one bus, so the address and data bus are multiplexed. Whereas here there are separate bus, so you can parallelly access the data and program memory. Okay. So typically the code memory is a read memory, read only memory, and data memory is a read write one. Okay. That's why it is impossible for program content to be modified by the program itself. Okay, that is very clear. So basically you can say there is a separate program memory and there is a separate data memory. Whereas in this case both are same because there is only one bus. So since program memory and data memory are separate, they can be accessed in parallel. So that's why the speed will improve. Okay. Then what is the problem? When there are more separate access of program memory and data memory, obviously the chip area will increase because there are separate address and data bus. We are not multiplexing. So if chip area will increase, the cost will increase, the power consumption will increase. So that's why the price paid is the increase in chip area. That's why, and therefore power consumption, therefore cost. Okay. So many modern CPUs nowadays, whatever CPUs are coming out, they have both Harvard and von Neumann characteristics. Basically, the separate on-chip instruction and data caches have Harvard type interface, while the common off-chip cache memory is interfaced through a single system bus. So it's something. Let me see if I have shown it or not. I think I have not shown it. Okay. So essentially what happens? So in a Harvard architecture, there are two levels of memory. General. Sorry. What I am trying to talk about the last point. Okay. So nowadays, the common practice of designing CPU is that the internal data and instruction memories follow Harvard architecture. That means separate data and separate instruction. Whereas there is another memory which is external to the CPU, which is accessed through a von Neumann architecture. Okay. So basically there are cache memories. We'll discuss about cache memory later. So internal cache is based on Harvard. The external cache and external memory is based on von Neumann. Okay. Hope now it is clear. So what is there inside a CPU? This probably everybody knows. Okay. So if I think whenever anybody starts studying about computer, they'll start learning that okay, CPU consists of one ALU, one control unit, like that, right? So here you also it more or less is there, but there is a little bit more to it. Okay. So CPU has a control unit and one data path. Okay. So basically it is a data unit, it is a control unit. So in this data unit, there is ALU. Basically data path is related to processing of data. Okay. So where data processing happens? Obviously, if you issue some instructions, say add some register to another register, what happens? You need registers, and those register content finally goes to the arithmetic logic unit, and the operations happens there, right? So the ALU performs the desired operation, and the output of the ALU is either stored in register or memory. That's why data path should have the register. Okay, and the various status flag. For example, when you add two numbers, there is a possibility of carry. When you subtract, there is a possibility of borrow, and the result may be 0 also, right? These status flags are basically used for other conditional operations later. So the status register should also be there, and these status flags are stored in that. Okay, so these are part of the data path. Then the control unit, what happens? Here once the instruction is issued, then the operation can happen in the data path. But which instruction to issue? From where we'll get it? So there is something called program counter register. So it is called PCR or PC, program counter. So program counter points to the address from which the instruction has to be fetched. That is, the next instruction has to be fetched. So once the instruction is fetched, it is stored in another register called instruction registers. And then from the instruction register, the instruction is decoded. Okay, so for example, add x comma bx. This is the x86 instruction. So this has to be interpreted in the language of ALU, right? What to do. So that's why there is something called instruction decoder, which will take the instruction from the instruction register and decode it and feed to the ALU, like the data path. So the PCR, the program counter, so that means from where to fetch the instruction, then the unit which fetches the instruction, the unit which stores the instruction, that is called IR, and the unit which decodes the instruction, these are part of the control path or control unit. Whereas ALU and the registers, these are part of the data path. Now, once the instruction is fetched and decoded, what happens? It goes to the data path, right? So there must be some bus, and that bus must be bidirectional, right? So that's why there is a bus which is interfacing the control path in the data path. Okay. Now, control unit always sends the PCR, which is basically PCR content is an address. So it is a unidirectional. So once it sends to the instruction memory, then the instruction is fetched from the memory. That memory could be instruction cache, that memory could be external memory, instruction memory, as we discussed in case of Harvard and von Neumann. So whatever it may be, then instruction is fetched, then it comes to the instruction registers. That's why this is the direction is from PCR to outside, whereas the direction for this IR is from outside to the instruction register. And here we are sending the address through the address bus. Okay. Now you send the instruction address, then you fetch the instruction, you decoded the instruction, then you send to the data path. In data path, the operation happened in the ALU. The output was stored in the register. Okay. Then, depending upon the instruction, you have to do whatever the instruction says. So here there is one catch also. So instruction may say to fetch the data in the register as well. Okay. So the part of the instruction may require a memory access. That's why here we are accessing the instruction memory, remember. But here, after instruction is decoded, we have to access the data memory, right? So we are sending the data address here. So now data address went out like through the address bus, then the data came through the data bus. Okay. Now the data came. If it is a memory access and memory read, the data came and it is being used. Now say it is a memory write. What will happen? The output has to be written to the memory. So that's why then the data will go out. That's why the data bus is bidirectional. Here also it is bidirectional because from the register a read can happen or to the register a write can happen. Okay, so this is a very high level view of the operation which happens inside a computer or the CPU. Okay, so we talked about instruction decoding, right? So essentially an instruction processing operation happens inside the CPU. Okay, so it has its own phases or stages, I would say. So here we saw that instruction is fetched and stored in the instruction register. Okay, that is provide the first operation. Then instruction has to be decoded, right? Then instruction has to be executed. So these are the primary three stages. So this is something called fetch, decode, and execute. Okay. So these stages can be further divided into multiple sub-stages. For example, we can have 5 stages like fetch, decode, load, execute, and store. Right? This can be done. What we are doing is, this particular phase we are dividing into multiple stages. So execute stage became load, execute, and store. So it depends upon the designer how many instruction processing stage it can have, but definitely it will have minimum of 3 such stages, that is fetch, decode, and execute. So these operations happens, if you see, sequentially, right? So first instruction is fetched, then instruction is decoded, then instruction is executed. Now in this case what happened? Fetch happened, then decode happened, then load happened, then execute happened, then store happened, right? So similarly, so it depends upon the CPU architecture, and the duration of each instruction may vary because each of these stages may take different amount of clock cycles. For example, this execute particularly may take different amount of clock cycle. The decode also may take, even the fetch may take, because if the instruction widths are different, so one instruction may require 2 bytes, one instruction may require 1 byte. So fetch, the timing, that means the clocks required for fetching the instruction will also differ. Okay. So again, we'll continue with the instruction processing. So each instruction consists of an opcode and 0, 1 or more operands. Okay. So for example, move AX, BX. This is basically an x86 instruction. x86, you know, it is an Intel architecture. Okay. So here, move is the opcode, and AX and BX are operands. Okay. That could be one instruction, for example, who may not have operand, for example, NOP. So this is nothing but don't do anything. So it doesn't have any operand. Okay. It's only opcode. Okay. And there are different types of addressing modes also. So basically it is not a microprocessor class, so I cannot really talk about in detail about all these things that I assume that you are aware of. You would have studied the microprocessor related courses before. But briefly I'll just talk about. Okay. So addressing modes are the way CPU accesses the operands. For example, add AX, 5. This means AX equal to AX plus 5. So AX is a register, by the way. Okay. So it is a x86 register. So this is called immediate addressing mode. Means here directly we are taking a constant, that is a number, and using that in this instruction. Now, sub AX, BX. What does that mean is AX equal to AX minus BX. So whatever the content of the BX is there, you subtract that from the content of AX and store that in AX. So here we are using the registers and we are using the register content directly. Okay. So that's why it is called register direct mode. Similarly, there is one more mode called register indirect mode, where what we are doing here is AX, you can see, then bracket, square bracket, BX, the BX is in square bracket. What that means is the content of BX indicates a location, that is memory location, where the data is there. That means the BX contains the pointer of the particular data. Okay. So what does that mean? This instruction means AX equal to AX plus the content of the memory location which is there in BX. That means the content of the pointer. Okay, that's why I mentioned star BX. Okay, so there are similar addressing modes, and these addressing modes differ from CPU architecture to CPU architecture. Okay, and this is about addressing mode. Then there are two principal techniques for implementing the control unit. If you remember, this is the control unit. So Okay, so where the program counter is there, instruction decoding is there. So primarily we are talking about instruction decoding here. Okay, so the instruction decoding has two ways of doing it. One is microprogramming. When in microprogramming, what happens? Every instruction consists of a sequence of primitive hardware commands or micro instructions for activating the data path. Okay, that means it's something like a there are small micro codes, and each instruction is translated to such micro codes through a table. Okay, so this is suitable when number of instructions is very large, and in fact the length of the instructions is varying. Okay, and here instruction processing is slower because it should go through a lookup approach, basically lookup table approach. Whereas the other way of doing it is the hardware logic. Okay, so here each instruction is mapped to some combinational and sequential logic hardware. Means each instruction maps to a direct hardware implementation. Here it was not like that. It was mapping to some microcode, which was again mapping to some hardware. Okay, here it is directly mapping to hardware, but it is suitable when the number of instructions are small, because if there is a large number of instructions, you require a large number of similar hardware, which will increase the chip area, and sometimes if it is huge number of instructions, it may not be possible to implement that also. Now, since it is that the instructions are directly mapping to hardware, the instruction processing is quite fast. Okay, so essentially, if you see in practically the CISC architecture. We'll talk about CISC architecture. CISC architecture more generally they use microprogramming because number of instructions are quite high. Whereas the RISC architecture use generally hardware logic. Okay, and there is one more thing I mentioned here. Nowadays, particularly, majority of the processor, or I would say all of the processors, are using a mode called slowdown mode. It is to conserve the power, because power is the biggest problem nowadays. So there are specific instructions which enable such modes. In such mode, what happens? The voltage and or frequency of the processor are lower, reducing the power consumption, because when you increase the voltage or you increase the frequency, the power consumption increases. So in some cases, wherever suppose some part of the CPU is not being used properly and all, there is no point in keeping it on all the time. No? So you reduce the voltage, you reduce the frequency, then some functionality of the processor may not work, but if that is not required at that particular time, why to unnecessarily waste the power? So modern processors are having a mode called slowdown mode as well. Okay. So we talked about instruction processing. So if you see this fetch, decode and execute, then we saw that fetch, decode and execute can become 5 also. So the number of stages in instruction processing lead to a concept called instruction pipelining. Okay. So primarily there are 3 stages: fetch, decode and execute. So it is called 3-stage pipeline. And there is a 3-cycle latency. Okay, so we'll take an example. So say for first instruction, the instruction is fetched. Okay, then it got decoded. At the same time, fetch unit is free, right? So the second instruction can be fetched when the first instruction is getting decoded, right? Then at clock 3, the first instruction got into the execute stage. Now the second instruction has been already fetched and the decode unit is free. So the second instruction can get into the decode fetch, right? And now since the second instruction is already fetched, the fetch unit is free. So the third instruction can get into the fetch
unit, right? So we are not wasting time. We are utilizing the free units of the pipeline to reduce the latency, right? So now what has happened? The first instruction is done at t plus 3, t plus 1, t plus 2. So okay, so this is t plus 1, this is t plus 2. So at t plus 3, the first instruction is done. Now at t plus 4, the second instruction is done, and at t plus 5, the third instruction is done. Now if we would have done it sequentially, how much time it would have taken? 3 into 3, that is 9 cycles. Now we finished it in 1, 2, 3, 4, 5. 5 cycles we have finished. It happened because of this instruction pipeline. That is something like a pipe. So from one end, in a pipe, what happens? In one end the water enters and the other end it comes out. Similarly here the instructions enter in one end and comes out in other end. So when in between the units are free, the instructions which are coming in, they occupy them, thereby utilizing the instruction pipeline effectively and reducing the execution of the instructions, total execution of the, reducing the time for executing the instructions. So this is a good thing, definitely, right? But it has its own disadvantages. Advantage we saw, it makes the processor fast, but there are some disadvantages which are called hazards. Okay, so these are called pipeline hazards. In pipeline hazards, and what are these hazards? These occur when a single piece of hardware is used in more than one stage of the pipeline. So it is possible for two instructions to need it at the same time. So for example, you see, for example, this execute. So execute, this stage may be required by, suppose this fellow requires the execute stage for 2 cycles. At the same time, this fellow may require it, right? So one instruction has to wait for that. Similarly, suppose if there is any one memory unit is there, which is shared by subsequent instructions, then one has to wait for the previous instruction to complete. So this is called structural hazard. And there are data hazards. Data hazards are related to modification of the data. So when read and writes of data occur in different order in the pipeline, then this data hazard occur. For example, RAW, that is read after write. It occurs when one instruction reads the location after an earlier instruction writes new data to it. But in the pipeline, the write occurs after read. Okay. So for example, the first instruction has to modify a particular register, but that has not done yet. But the second instruction is a, say, smaller instruction which has already gone in and read that particular register. Then it will get the old value, right? So that's why this is a hazard. So this has to be prevented. So similarly, there is write after read. So a write occurs after read, but the pipeline causes write to happen first. So a write has to occur after a read, but in pipeline what has happened? Read has occurred earlier, so write has occurred later. So again, the write data is not be getting reflected in the system. Write after write. So two writes occurs out of order. So first one writes initially. Suppose there are two instructions. The first instruction has to write to a register or a memory location first. Then second has to modify it. But it can happen in a alternate way also, right? Then the whole operations will result in some incorrect value. So in order to resolve this hazard, we cannot allow this hazard to happen. So pipeline stall has to happen. Means in the kind of cases should be detected. Then we should stall the pipeline. That means the instructions should not move in that pipeline till these conditions are resolved. Then only we should allow the pipeline to operate again. For example, if there is one instruction which modifies a particular memory location and then the other instruction has to read it, but the other instruction has already finished its other operations and waiting to read, and the first instruction is still has not written it, then in that case we will not allow the second instruction to proceed further It will wait for the first instruction to complete the write, then only the second instruction will allow to read it. So that is an example of pipeline stop. Okay. Now we talked about structural hazards, we talked about data hazards, then we'll talk about control hazards. So it happens when a decision is made. For example, if then else condition. There is a in if then else condition, what happens? There is a jump instruction, right? So in case of a jump, what happens? If you see in a longer pipeline, the instructions are being fetched really. Okay. Now it encounters one jump instruction. So if the jump condition, the condition for the jump is satisfied, then it has to jump to a place. Otherwise, it will continue in the same order, right? So if the condition is satisfied, then what happens? The next instruction which has to be fetched is there in some other place. So that instruction has not fetched yet. Whereas some other instruction which are actually there subsequent to the jump instruction, they have been fetched and some of them have been executed. Then it is a waste of effort, right? So the entire pipeline has to be flushed in that case, and the new instruction were to be fetched, right? So this is a control hazard. So it basically delayed the entire operation for a long amount of time. So whatever you have done, it has to be flushed out and it has to restart from the new location again. Okay. So this is resolved in different ways, in different architecture. Sometimes it is assumed that the jump will not be the condition will not be successful, so current instructions are fetched and executed. If the condition is true, then and the entire pipeline is flushed. In RISC architecture, there are some other way to handle it. It is called delayed batch. Okay, so there are different ways in different architecture to handle it. Okay, but this is a hazard. So these are some of the disadvantages of the pipelines, instruction pipeline in these modern CPUs. Nowadays, the depth of the pipelines are quite high. So in some processors, there are very long pipeline which are called super pipeline processors. Now let us see, where do processors spend more time? So this is a data which has been taken from the book Skip Forward, ARM system on chip architecture. Okay, and you can see that the data movement instruction constitute 43% of the processor time. The control flow instruction, data movement means basically the instructions which are related to read and write to the memory. Okay, these are data movement instructions, or you can say load and store instructions. Then control flow instructions are basically the jump instructions. In C, if then else or switch cases, these statements translates to this control flow kind of instructions. So they spend 23% of time. The arithmetic operations, which are plus, minus, multiply, divide, etc., increment, they spend 15%. Comparisons are all, greater than, less than, equal to, checking whether two register values or two numbers or two memory locations or one register value or memory location, they are equal or greater than or less than, etc. They take 13% of time. Logical operations and or XOR, etc. These takes 5% and others take 1%. So generally, computer is known to be the device which does arithmetic and logical operations, right? People generally understand that. But if you see, the CPU is spending more time in the instruction related to data movement and related to control. In fact, the arithmetic and logical operations, total 20% of the time will be there taking. So that is the reason
the computer, the architects, they try to optimize the computer, and they found out that better to optimize this part, okay, so that the CPU become faster. So that's why different type of processor architecture came into picture. We talked about von Neumann and Harvard, which are primarily based on the primitive way, or I would say initial way of designing computer. But then as the CPU design went on, the processor design went on, the different types of features have been added. So based on that, there are two types of architecture. One is called CISC processor architecture, and another one is called RISC processor architecture. Okay. So the CISC processor architecture. So CISC stands for Complex Instruction Set Computer. So here instructions are of variable format and length. This is not a fixed format. So that's why large number of instructions are there. So practically any instruction can reference memory here. So instructions can reference to memory. Single set of work register. There is a single set of register, and all of them are used for these operations. So because large number of instructions are there and they are variable format and length, it cannot be hardware. So we need to have a microprogram instruction decode logic. I talked about it, right? So the complexity of instruction is handled at this level. Okay. So great varieties of our addressing modes means we talked about, right? Practically any instruction can reference memory. So there are different types of addressing modes, large number of addressing modes, and no instruction pipeline. Actually, nowadays instruction pipelines are being added, but primarily, if we are talking about the CISC processor architecture, theoretically there is no instruction pipeline. But nowadays in CISC processors there are pipelines as well. So why all these things? Basically, it is to reduce the effort of programmers coding. Means programmer does not have to write more code. What does that mean nowadays is compiler is simpler for this architecture, because there are so many instructions. You can directly map the high level language to the low level language easily. Okay. The example is x86 architecture, that is the Intel processor architecture. They are all CISC architecture. Okay. The RISC architecture is they try to do the this particular I have shown here this particular table. So where it is they measured which part of the processor is taking more time, so they try to optimize it. Okay. So in RISC, that's why they thought it is better to reduce the number of instructions so that the instruction decode logic will be faster. Okay. So that's why reduce instruction set computer, and the instruction size is fixed. This 32-bit. Now we have fixed the instruction size, that is length of the instruction. Whereas remember in CISC it is variable. Okay, the instruction size can be anything. And here it is 32-bit. Now we have the number of instructions are less. Obviously you are trying to make use of hardware instruction decode logic, right? And the load and store architecture, that means the instruction operating on data and operating on registers, they are actually separated. Okay. So no ALU related instruction will be accessing memory. They will be operating on registers only. So that way, again the instruction decode logic is simple if they are not accessing memory, right? And there are separate instructions which will access the memory. So these are all load and store instructions. So that's why it is called load and store architecture. And since what we have done is we have put so many restrictions, so we need to have a large register bank. Otherwise, the instruction cannot operate. Now we are not allowing the instruction to access the memory. So they have to operate on different registers. So we need to have more registers, right? So because such restrictions are put on the instructions, so it is easily implementable using a hardware instruction decode logic, thereby making the instruction decode faster. Okay. And there are pipeline execution. and it is actually there is a single cycle instruction, single cycle execution. The way the RISC processor is designed in such a way that all instructions complete in single cycle. There are few exceptions, particularly multiply kind of things, which probably cannot, but in generally in the current RISC architecture. So because of all these things, the performance is enhanced. The example is ARM architecture. So these are RISC and CISC. So for real-time purpose, generally this RISC architectures are used, and the most popular processor which is used in various real-time systems is ARM. Okay.